All right. Well, as you can see, today's notes are going to look a little bit different just because we are going to be using the graphing calculator for part of the notes today. So I wanted to make sure that you were able to see kind of everything that I'm doing on the calculator as we get to those parts. Now, the first part of the notes today, we're going to focus on describing some quantitative data using what's called SOX. So we're going to kind of develop what SOX is and kind of why we use it to describe data. So Brian and Jessica have decided to move and are considering 7 different cities, which I've got for us below. The dot plots show the daily high temperatures in June, July, and August for each of those cities. We're going to help them pick a city by answering some questions that they've got for us below. So the first question, what is the most important difference between cities A, B, and C? So as you take a look at A, B, and C right here, notice that really their dot plots look kind of the same. The one difference is kind of where they're located. Basically, all of this data is between, it looks like about maybe 75 and 100. And so really, let's just talk about where the center of the data is. It looks like the center of the data is around 90, whereas the center of the data for B would be around maybe 68 or 69, and the center for the data of C is somewhere around 80. And when we talk about center, what we're really talking about is the average. In other words, the average temperature for city A would be around 90, for B would be around 69, and for C would be around maybe 80. So the most important difference is kind of where the center of the data is located. In other words, what the average is for each of those different cities. Next, we want to talk about cities C and D. So what is the difference between what C looks like right here and what D looks like right here? Well, pretty clearly, they don't look the same. In fact, I mean, if you think about kind of where those are, the center is actually probably about the same. If we want to think just about kind of what the average is, the average of the middle of the data for D is probably right in here. And so they're both kind of right around 80. But you can see that one is a lot more spread out, which is really important because obviously with C, you're a lot more consistent. You're kind of between these two values, whereas D, you've got a lot of extra data that's outside of those. So you've got a lot more kind of spread in our data. It's a lot more spread apart. And that word that I keep repeating is the most important difference, which is that we should probably talk about the spread of the data. The third one, what is the important difference between cities D and E? So now we're looking at this city right here and this city right here, which really, when you look at those two, once again, the centers are about the same. Between D and E, they both have centers right around 80. But when you're looking at those, one of them, and if you wanted to talk just about spread, I mean, technically, they're between the same values. If you look at kind of those 2 points at the very ends, you're right around the same temperatures. So what's really different about number 3 isn't so much the spread as it is kind of those 2 points which kind of cause that to happen. And those 2 points are a lot different from the rest of the data. There's these big gaps in between the rest of the data and those points on the outside. And so those points on the outside, you may have heard this before, they are referred to as outliers. Now, with outliers, we typically also talk about other what we call influential points. So when we talk about those, just know that we are talking about kind of any points which would influence our data. All right, finally, number 4. What is the important difference between C, F, and G? Okay, well, here's C. So you're looking at this data right here. You've got F, which is this data right here, and G, which is this data right here. Which really, when you're looking at those 3 different graphs, the centers, once again, are about the same. They're all kind of centered right around 80. In fact, their spreads are also the same. Notice that, the distance from here to here is the same as the distance from here to here, and that's the same as the distance from here to here. So it's not the centers, it's not the spread, it's not even outliers. Notice that really there aren't any outliers for those? Yeah, I mean, we've got some points over here, but there's not huge gaps like there were for graph E. So really what makes those different, if you look at them, is just the shape of the graph. You've got one that's kind of symmetric, one that's got kind of this tail going to the right, another that's got this tail going to the left. And so rather than talking about the center or the spread or the outliers, we're going to say that for number 4, the most important difference is the shape of those 3 graphs. So there's basically 4 things then that we've decided that we need to talk about when we're describing a distribution. One of which is center, the other is spread, the third is outliers, and the last is shape. To help remember those, we're going to use an acronym. We're going to talk about what's called SOX. So SOX is a way that you can remember those 4 things. The first S we'll use to talk about shape. The O we'll use to talk about outliers and other influential points. And then the third is center, so where the center of the data is approximately. And the last is the spread. So again, that acronym of SOX, S-O-C-S, there is no K, so yeah, it's not quite that much fun. But it's just a nice way to remember what those things are that you need to talk about in order to make sure you're discussing all the key characteristics of a distribution. So let's first talk about the shape, because there are some different shapes that we're going to want to consider. The first is what's called symmetric. So symmetric basically means that the data can be divided into 2. Symmetric can look like a lot of different things, but most oftentimes we'll think of symmetric as being this kind of bell-shaped curve, where if you were to draw a line down the middle and cut it in half, it would look the same on either side. However, you can also have symmetric data, which is not bell-shaped, and we'll see some examples of that a little bit later on. The next is what's called skewed to the right. This is also sometimes called right-tailed. And right-tailed is probably the easier way to think about what that's going to look like. It's going to have kind of a bulk of data over here, and then have a tail that stretches out to the right. So most of your data is to the left, but then you've got this tail to the right. That's going to be what skewed right looks like. So you can probably guess what skewed left is going to look like. It's very similar, except this time your tail is on the left side of your data. And so again, skewed left, you could also think of as being left-tailed. Again, the appropriate way to say those is to say skewed right and skewed left. But if you want to start by saying right tail and left tail until you get used to that, that would be okay for right now. All right. So unimodal basically means that there is just one peak to the data. So similar to symmetric, that would be that there's just kind of one highest point at the very top of our data. Whereas bimodal is going to mean that there are 2 peaks. So you're going to have maybe one peak over here and the second peak over here. And again, what we're saying with those 2 is not necessarily that they are the same height, but there are 2 different peaks or 2 different modes to the data where those are occurring. Bimodal can also be symmetric, so if you want to think about kind of what that would look like, a symmetric graph can also be bimodal if it has kind of 2 peaks, where if you were to cut it down the middle, it's still symmetrical on either side. So in this case, the first one I drew is not symmetrical because the left peak is higher than the right peak. However, in some cases, you might have a bimodal graph where the peaks are the same height, in which case it might also end up being symmetric. Now for uniform data, you kind of want to think about almost like a school uniform or a team uniform where it's made so that people look the same and look part of the same team. A uniform distribution is the same idea, is that the height is kind of the same all the way across the data distribution. That would be an example of uniform. All right, so what is the most important thing to remember when you compare 2 different distributions? Probably the most important thing is to do it in context. So make sure you compare the data in context. Otherwise, all you're really doing is talking about the numbers and the shape, and unless you're really giving the context of it, the comparison really isn't going to mean a whole lot to someone just casually reading the description that you've written. So let's take a look at some examples here. So for this first example, how did the annual energy costs in dollars compare for refrigerators with top freezers versus refrigerators with bottom freezers? The data below is from the May 2010 issue of Consumer Reports, which unfortunately, the way they set this up was not very well done. They actually put the bottom freezer data on top and the top freezer data on bottom. I don't know why they decided to do that. It's kind of annoying if we're being honest, but it is what it is. So let's do this first. Let's go ahead and just do a simple SOX analysis for both, and then we'll write a comparison kind of in a more paragraph form. So we'll use this for the bottom freezer setup. We'll also do one for the top freezer setup. So again, SOCS. Okay. So talking about the bottom freezers first, so that's kind of this data on top. Let's talk about shape. And as you're looking at the shape, I would say it's either going to be symmetric or really because of those kind of what we'll talk about as outliers, I would say that the data is kind of right skewed or right tailed. Now, in addition to that, let's talk about those outliers. So it looks like we've got two different outliers, one of which is around 140, maybe 141. I'll just say 142. The other is a little bit past that, so maybe at around 150. So we've got two outliers to talk about. The center for the data, we'll look for kind of where's the middle of the data, which looks like it's about here. It looks like the center is around 70. And for spread, let's just talk about the range. It looks like for spread, you've got it going from maybe about 42 all the way up to 150. So your range, remember, go from max to min. 150 minus 42, your range is about 108. All right, now let's go ahead and talk about the top freezers. So when we're looking at the top level freezers, the shape in this case, I would say you could either say that it was more uniform. I'm just going to say that it's symmetric. Either one of those would probably be okay as a description. For outliers, there aren't any, at least none that I can see where there's a big difference between the two. For the center of your distribution, it looks like our center is kind of right here around 56. And then for your spread, you're going from, again, about 42 this time to a little bit less than 70, so maybe 42 to 68. So your range then takes 68 minus 42. It's going to be about 26. All right. So now, taking a look at kind of those two different shapes, we now have to write our description of those. And so to write our description, let's first compare the two different shapes. We'll say that bottom freezers are skewed to the right, whereas top are more symmetric. Let me rewrite that because I know that didn't look good. So are more symmetric. For outliers, we'll say that there were two bottom freezers had an extremely high energy cost. I'll just say extremely high cost there. We'll also talk about centers. So on average, it looks like bottom freezers cost more than top freezers do. And again, that's because the average for bottom freezers was around 70, whereas top was 56. There's also more variability or spread. Oops. for the bottom level freezers than for the top level. All right, so notice that we're putting kind of all of that into context. That'll be important again to make sure that you're doing that whenever you're looking at this data. All right, so in this last example, we're going to talk about stem plots. In fact, this would probably be a good place to stop, so we actually probably won't need the graphing calculator for this video. But in the next video, we will be using the graphing calculator quite a bit. We'll be using it to talk about how to create a stem plot, as well as how to create what are called histograms. So we'll talk about kind of those two things in our next video. Until then, have a good rest of your day.